So let us solve some problems on 2D analysis. We want to find the temperature field of the following scheme. So we have in this problem a repetitive pattern in which we have an air channel that is within a combustion gases flowing at T infinity and convective coefficient H out, plus you have air channels within the system. So you have two flows, inner and outer sides. Okay. You have the following solid channel, and you have from the outer side combustion gases at a certain temperature T infinity out with a convective coefficient H out. And also you have a flow from the inner side. You have an air channel at T infinity in and H in. And you want to solve for the temperature variation within the solid material. So this is our domain. So this is the solid is limited in the following zones. And of course, to be able to solve and simplify solution, we try to identify if there is symmetry. Because if you have symmetry, you can reduce a lot the computation. Already you can say, I need to solve temperature in this domain. Okay, I need to try to reduce the domain as much as possible to facilitate the solution. So I can look first if I have any symmetry. First, I can see that this is a symmetry line. So I can study this part and I can deduce by symmetry temperatures in the other part. You can also say that if I consider the remaining part, also I have a symmetry about this axis. So I can say that I can study just this part. And finally, you still have an axis of symmetry here. So you can say that the domain to study is this one. I can just study this part. Okay. So in this way, I simplified a lot my analysis. Once I solve for temperature in this part, I can deduce by symmetry temperatures here and then here, etc. And I can find for the repetitive pattern how will the temperatures vary. Now keep in mind, whenever you do a symmetry line, then you can say that along the symmetry line, the heat flux is 0. So you can say that for this side, I have Q second equals to 0 because it's along the symmetry plane. Same for this side here, okay? And same for this side. So for these three sides, you can say that Q second is 0. You just have now, as boundary condition for the other surfaces, you have convection. So for this surface, you have convection at T infinity out, H out. And for this one here, for these two surfaces here, you have a contact with the inner fluid. So for these two surfaces, you will have T infinity N H. Okay. So let us draw again the domain to have a clear view of the domain. So this is our domain to study. Okay. As we said, along symmetry lines, we have adiabatic conditions. So we can represent again the conditions. So for this line, this one, and this one, we have adiabatic conditions due to symmetry. So for all of these boundaries, Q second is equal to 0. And here also, Q second is 0. Now, we have convective condition for the other faces. So here we have convection with the outer fluid. And for these two sides, we have convection with the inner fluid. So this is the first step of identifying the domain and considering the boundary conditions. Okay. Now, next, we need to determine how many cells we need. Okay, so we need to divide the domain into several cells, and we need to write for each cell the equation, the energy equation. Okay, so to start with, first we need to decide on delta x and delta y, the grid side. Here they can give us the grid size. So for example, if they say use a uniform grid size in a way that delta x equals delta y equals to 1 millimeter, then depending on the dimensions that we have, we can decide on the number of nodes. So here, according to this figure, okay, you have that this distance is 6 millimeters. So when you divide into two parts, you still have here just 3 millimeters. So this side is 3. Then you can consider that if I have delta y equals to 1, I will have to divide into 3 cells. Okay. Uh, Now it depends also if you want, the number of cells will depend if you want to consider for your cells, for your extreme cells. As we know, we have two approach. We can consider for extreme cells a size of delta x over 2 and delta y over 2. If you use this approach, okay, then for the cells at corner, so in this case, they did this approach. They consider that whenever I need to take nodes at the extremity of my domain. If you choose to do this, okay, then you need to consider for extreme cells sizes of delta y over 2. So for a corner, you have delta y over 2 and delta x over 2. Okay, and for normal cells inside the domain, you have delta x and delta y. Okay, do you hear me?